Hi, welcome to my presentation. My name is Chen. I'm a PhD candidate in chemical engineering. My topic is to produce clean hydrogen by water electrolysis, the hydrogen evolution reaction. Hydrogen is the most fundamental chemical in modern industries. It can be used in hydrogen vehicles and synthetic fuels to reduce tons of greenhouse gas emissions. It is also important to many industries, such as ammonia production and metal refining. The conventional hydrogen production process is hydrocarbon reforming from natural gas. It is more profitable but not sustainable. For example, the hydrocarbon reforming process in ammonia synthesis accounts for roughly 1% of global annual CO2 emissions, more than any other industry. An alternative way is to produce hydrogen by water electrolysis. This reaction only requires water and electricity, and the whole process could be carbon dioxide free if the electricity comes from renewable sources. The challenge of water electrolysis is it's almost twice expensive than the conventional process. The cost mainly comes from two parts, the electricity and the catalyst. Actually, they all associate with the electrocatalyst. Theoretically, the water can split into hydrogen and oxygen under 1.23 volts, and the hydrogen evolution reaction happens at 0 volts versus RHE. This is true in thermodynamics, but kinetically, the reaction needs excess energy to push it forward. So an electrocatalyst is needed to reduce the energy barrier. This excess energy is called overpotential. A larger overpotential means you need more electricity to get the same amount of hydrogen gas. The platinum is a benchmark. It is highly efficient toward the HER, but the only problem is the material is too expensive. So the ideal electrocatalyst should have a small overpotential to save electricity, and also has a low cost for the material. Therefore, we're trying to develop a cobalt lithium phosphorus titanium composite that meets these requirements. We use electrodeposition to fabricate thin-film materials. Cobalt, molybdenum, and phosphorus will be reduced to the element state and grow on the substrate. Because of the surface charge, TiO2 particles will be attracted to the interface and embedded into the deposit. Deposit's composition can be easily controlled by adjusting the electrolyte. We started with pure cobalt and then improved it step by step by adding molybdenum, titanium particles, and phosphorus, and finally obtained the cobalt molybdenum phosphorus titanium composite. These deposits were tested for HER in 1 mole sodium hydroxide. We began our work with pure cobalt because it is one of the active transition materials toward the HER. But take a look at the polarization curve. We usually compare the eta 10, which is the overpotential at 10 milliamps per centimeter square. It is 5 times larger than platinum. To enhance the electrocatalyst, we adopted a theory of Trasadi's volcano plot. That is, for a catalyst, the bonding energy between hydrogen and the metal catalyst should not be too high or too low. In this plot, the platinum is among the best single metal catalysts, for it has a suitable hydrogen bonding energy. And the cobalt's hydrogen bonding energy is too low. But if we combine two metals on each side, for example, cobalt and molybdenum, which has low and high bonding energy respectively, we can obtain an alloy that has suitable hydrogen bonding energy. We found the overpotential of cobalt molybdenum is significantly reduced, but still a little far from the platinum benchmark. Our next step is introducing TiO2 particles into the deposit. We do this because TiO2 can absorb the hydroxide generated by HER due to the balance of particle surface charge, and thus buffer the local pH. According to the Volmer-Hirovsky mechanism, we derived an equation that shows a lower surface pH can lead to a higher reaction rate. The cobalt molybdenum titanium showed a further decrease over potential of 68 millivolts. The last thing to do is add phosphorus in deposits. Phosphorus is well known to lower the Gibbs free energy of the HER. It can also slightly alter the reaction mechanism by changing the surface hydrogen coverage. In this way, the cobalt-molybdenum phosphorus titania showed a remarkable overpotential of 31 millivolts, even lower than the platinum thin film deposited under the same experimental setup. Moreover, cobalt-molybdenum phosphorus titania also shows a good stability. Look at the green line. It has more fluctuations of potential over time, reflecting a larger gas bubble generation. And its polarization curve overlapped very well after 48 hours galvanic static stability test, indicating good stability, not like the other two drifted to more negative values. Finally, we have to take a look at the surface area because the overpotential is surface area sensitive. We assess the electrochemically active surface area by comparing the limiting current density of the ferricyanide redox reaction and the mass transport control. We found the particle increased the surface area by 20%, and the phosphorus did not change the surface area. But anyway, this is a minor change compared to the large improvement of the overpotential. SEM image also showed a crack-free and relatively smooth morphology. To summarize, we obtained a cost-effective electrocatalyst which has good performance and stability. We hope this development can help the hydrogen industry to produce hydrogen in a sustainable way at a more competitive price. I thank Clarkson University and NSF for the funding support, and thank you for your attention. Please feel free to ask me questions.